Alright, so now we're going to talk about solutions that are formed when we have our liquid solvent, and then we drop a solid solute into it and get it to dissolve. Or maybe not, in which case you don't get a solution. So we're going to call back to a little bit of stuff we briefly touched on in Chapter 6, which feels like a lifetime ago. It was like 5 chapters ago. The nights then were probably hotter than the days are now. You know, it was a different world back then. But what we talked about then was that we had, we talked about concentration of solutions. We talked about molarity, right? How many moles of something there were per liter. And one thing I mentioned in that discussion was that there's a maximum amount of solute that you can dissolve. All right, so you can add, in this case, you add a solid, you stir, and it goes away. It dissolves. You don't see the solid anymore. All the molecules have dispersed in the liquid. So then you add some more. You add some more solid and stir, and it disperses, and some more. But eventually you put a scoop in there, and you stir, and it doesn't all go away. And then if you add another scoop, that whole scoop just settles to the bottom. It just stays solid. Because the solution has dissolved. The solvent can only carry so many dissolved particles. It's like a subway or something. Like there's only so many people you can fit on a train car, and then you can't anymore. So there's only so many molecules you can fit in the liquid, and then you can't, and so it just settles to the bottom. It waits for more liquid or something. So that was called a saturated solution. So we had a maximum amount of solute that can be dissolved by a given amount of solvent. And that's a saturated solution. How much solvent or solute that is, that's called the saturation point. So it's a saturated solution. You can't get any more solute to dissolve in it. So, for example, the maximum amount of sodium chloride that will dissolve in 100 grams of H2O I'm going to put a temperature on here, 20 degrees Celsius, is 36.0 grams, or 6.14 molar. The grams per 100 grams of solvent is kind of a standard way of measuring maximum solubility, but you can convert this into molarity by just assuming 1 gram per milliliter for the water, and that the volume of solute is negligible. So you say, this is 100 milliliters of solution, convert this to moles over liters, blah, blah, blah. But the main thing is just, there's a certain point. If I throw 37 grams of NaCl into 100 grams of water, one of those grams is just going to be salt crystals at the bottom, no matter how much I stir. I can put less in. I can put 18 grams. It'll all dissolve. And we have a name for that too. It's an unsaturated solution. So, if we have less, has less, what am I, Gollum or something? Alright, so if we have less solute, than the saturated solution, then it's an unsaturated. Again, as creative as ever with the names. And when we do get creative, it's not a good thing. Alright, no one wants creative names. We like systematic, saturated or unsaturated. You don't want like saturated or like bifold, right? Like you want the names to go together. So that's what we do. Alright, so there's a reason I threw a temperature here, by the way. the saturation point, the amount of solute, the maximum solute that we can dissolve, changes with temperature. Alright? So if we increase temperature for solids, this generally means that we're going to get an increase in solubility. Which means that if I heat up my water, I'll be able to dissolve more than 36 grams of NaCl. Now how much that changes depends on this substance. So it's not a huge change for sodium chloride, so I'm actually going to go to a different compound here. So for example, potassium nitrate is about 40 grams per 100 grams H2O at 20 degrees Celsius. So at room temperature you can get about 40 grams in there. But if you heat it up, you can get about 170 grams per 100 grams of H2O just by getting up to 80 degrees Celsius. So not even the boiling point of water, but pretty warm. Yeah. That's going to be more than a hot bath. Alright? So, we can get more stuff to dissolve typically by heating up the solution. Alright? So you stir in that solid, right? And it doesn't dissolve. And you go, oh, I've got a saturated solution. Well, if you put that thing on a stove and heat it up and keep stirring, you'll see that solid start to go away. And there's a neat trick too. If you can get it all to dissolve, and then you carefully cool the solution back down, and you have a nice smooth container, no scratches, it's like a nice new piece of glassware. Your lab partner hasn't had a chance to carve their initials into it yet, anything like that. Then if you cool it down gently, the solid doesn't reform. And so what you have is, there's like the saturation point, and then you heat it up, and you get everything to dissolve, and then you cool it down. And so the saturation point is actually below how much stuff is dissolved. So this is an interesting idea. And this is known as a supersaturated solution. So, again, creative as always with the names. So there's more solute than a saturated solution. And so what we can do is play on this idea of changing temperature to change amount of stuff that will dissolve. And now the key thing is you do have to get all of the solid to dissolve. If there's any undissolved solid, what happens is you cool it down and then you start seeing you have more solid at the bottom. You heat it up and there's less, you cool it down, there's more. But if you heat it up to the point where there's none, you've got a nice clean container, we'll talk about why that's all important in a second, you can get a supersaturated solution. Alright? So to prepare, you heat up solution to increase the saturation point, plus dissolve more solute. Then carefully cool back down. Okay? And that's important. So you get it hot, you increase the solubility, you get everything dissolved, and then you slowly cool it back down, and it stays dissolved. But what can happen is, well, actually, before I talk about that, so why this works, let's talk about that first. You've got your dissolved particles, they're moving around. A solid, they're stuck together, right? Dissolved, solid. Dissolved, solid, right? Movement, it's moving around in the solution. It's swimming, it's in the swimming pool, right? It's hanging out with the solvents, having a good time. Solid is like it's anchored at the bottom. It's not going anywhere. It's stuck to other neighboring particles. Well, there's a kinetic explanation for this. The particles have to catch and form a solid. And if they can't, if there's not an imperfection on the wall that holds it in place long enough for another one to come in, and then they become a solid together, and then it builds on that, it kind of dogpiles on, and then it doesn't happen. Now, if there's any piece of solid that's already there, then they just dogpile on. But if you can keep that first piece of solid from showing up by carefully cooling it back down in the right kind of container, it doesn't happen. It can't happen. But what's cool is, so you get that super saturated solution, also known as a supercooled solution. And if you throw one little piece of the solid in there, or any sort of imperfection that's big enough to create a surface for it to start forming, it can be instantaneous. Boom! It just solid forms fast. If you throw in a little piece of the crystal product, the original solid, on a super saturated solution, you'll see it grow. You'll see one big crystal form off of it if you do it right. So that's why that happens. Alright, now that's why we can't have any scratches, because the scratches are going to allow the solid to start forming. And so there are labs where students do, synthesis of aspirin or something like that I've taught, or alum, and they have to get a crystal product at the end, and that involves cooling the solution down, and then usually their solid starts to form. But every now and again, students don't have it form because their glassware is new. And so what I have to do is I go up and I just go with a little metal thing and I just scratch the inside of the beaker or whatever it is that they're waiting for the crystals to form in. And a lot of times it's just like I described. It looks like frost just showing up really fast on a piece of glass or something, on a cold day. I guess you guys can't really, I don't know if you can relate that here or not. But it's that fast. It's just boom, and then solid at the bottom of the beaker. And it all starts that scratch I make. Now, it does make a horrific sound because I'm scratching glass. So it's not like it's all fun and games. Like, it's a lot of people holding their ears. It's like, but it gets the job done. And if they have an old beat up, been around the block a few times, used and abused general chemistry beaker, they're probably going to get solid just fine. They don't need me to scratch it. So then I started accusing them of breaking their stuff too much if they have a brand new beaker. You can't win with me sometimes. Alright, so that's the effect the temperature has. There's a neat trick we can pull off with that. What about pressure? I didn't talk about pressure in my example. Why not? Well, solids aren't compressible, right? We've talked about the phases of matter. I put pressure on a solid. It doesn't really change volume very much. And as a result of that, and if you can read between the lines here that there is something that this does mean later, but because solids aren't compressible, pressure doesn't affect solubility. So changing pressure doesn't affect solubility. Okay? Alright, and then, IMFs. This is tricky. So, temperature, nice trend. Pressure, you can try to, you can take your solid and you can try to push it into the solution, and you can press it, with force as best you can, and it's just not going to do anything. It's not really going to compress. It's a solid, right? It's very dense. There's not really room for the particles to squeeze around each other anymore, and so you don't get a change in solubility. Intermolecular forces, well, it's tricky, right? It's the intermolecular forces of our pure solid versus the IMFs of the mixture. And so it's tricky, so we're not going to worry about it too much. But you know, we'll throw the phrase out with liquids like dissolves like. So solids that have matching IMFs to the solute, or the solids that have matching IMFs to the solvent, excuse me, are going to dissolve better than ones that don't. But it also depends on how strongly the solids are attracted to each other as well. And so, you know, there are ionic compounds that do dissolve in water, and there are ones that don't. The ones that don't have stronger attraction between the ions than the ones that do. So water is able to seduce sodium chloride apart because the sodium and the chloride aren't that into each other. But if you have, you know, something like magnesium, what do we have? Sulfide, that's not going to be water soluble because they're going to be more strongly stuck together. You have a +2, you're going to have a -2. They're going to have 4 times the attraction, roughly, of sodium chloride. Roughly, very roughly. And so they're not going to be very, very water soluble because it's tough to get enough waters around a magnesium and around a sulfide to get them to go away from each other. There's only so much surface area for the water to interact with. And same deal with covalent compounds. But, you know, for example, if I throw this marker, it's fine, Sharpie marker. It has the little stamp here that it conforms to some sort of standard that's incredibly small written, small writing. There we go. I don't know what it stands for. I don't know my ASTM standards either. But anyway, if I try to put this in water, it doesn't dissolve, right? So this is a solid that does not dissolve in water. It would surprise you to know that plastic doesn't dissolve in water. And that's because the intermolecular forces that hold the plastic together are going to be stronger than the intermolecular forces of the plastic interacting with the water. This is actually made out of non-polar compounds. Water's polar. They're not alike. They're not going to dissolve. But we'll build on that more in the liquids section. We talk about liquids dissolving in other liquids. For now, it's just, you know, eye on the ball with the solids. Increase temperature, more solid will dissolve. You can use that to cool it back down carefully, get a supersaturated solution. And the pressure doesn't really affect solubility. And intermolecular forces are too complicated to have just a general trend. So it's very, 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 very situational. Alright, so we're going to talk about gases next. We're going to talk about solubility of gases. And like I said, if you read between the lines on this one, you'll get a pretty good heads up on the next video and what I'm going to talk about there a little bit. Alright.